Hey everybody, and welcome to a video on section 7.9. You are watching this video because my daughter is sick and I am watching her in the morning. Before we get to section 7.9, I just wanted to reiterate from my email that you need to download an app on your iPad called Sage Math. And just so there's no confusion, I wanted to show you the logo for Sage Math. So you want to make sure you download an app that has this blue logo with a white geometric figure in it. I don't know the name of this. It's like a platonic solid of some kind, it looks like. But anyway, this is the app that you want. The reason you want this app is because starting on Friday, when you will bring your iPads to class, and I will show you how to use it, so you need it before Friday. But starting on Friday, we're going to spend a week doing math modeling, and the vehicle we are going to use to study math modeling is epidemic spread. So we'll study the spread of disease. And since we're going to be doing modeling, I wanted to briefly remind you the setup of modeling. So what does modeling look like? Modeling is a three-step process. The first step is to set up a model, just like we did in like chapter 2. You write down an equation or a set of equations that models or describes what you're interested in. Step 2 is to solve the model. So you solve the equation you wrote down, or you solve the system of equations you wrote down. Step 3 is to then interpret the solutions of that model in the context of the physical problem. So step 1, set up. Step 2, solve. Step 3, interpret. Over the next week, we are going to focus solely on steps 1 and step 3. So we're going to focus solely on setting up models that describe the spread of disease, and step 3, which is interpretation of the solutions. We are going to outsource step 2 to Sage. So we're going to let the Sage Math app solve these differential equation systems for us. The reason is because the systems of equations we need to solve we actually can't do by hand anyway. But even if we could solve them, I want to take a break from solving DEs and focus on the bigger picture, focus on interpretation and setup. And we'll let a computer do the heavy computational lifting for now. So I just want to switch the emphasis. Let's take a break from all of our, Laplace transform computational tedium, right? Let's let the computer do that and make sure we understand the big picture of how modeling works and that we can interpret what the computer tells us in the context of epidemics. Now, on to section 7.9. So what I'm going to do in this video is I will give you an overview of the big picture of 7.9. Then we will cover two examples. One example will show you how undetermined coefficients works, and the other will show you how Laplace transform works in the context of linear systems now. Right? So now we have systems of DEs that we are solving. So basically, section 7.9 says, hey, remember things like undetermined coefficients? Remember variation of parameters? Remember Laplace transform? Do you people remember these things that we talked about, 2 months ago? Well, guess what? They all translate to systems. So undetermined coefficients has its own theory in the context of systems. You can translate Laplace transform to linear systems. So we're just going to see how that works. So if we were in class, I would start by asking you, hey guys, do you remember, solving equations with these things? You, of course, remember these terms, don't you? Undetermined coefficients, variation of parameters, Laplace transform. And all of you would nod, yes. You would say, yes, of course we remember these things. You taught us these things so well, how could we have forgotten? And I would say that's the correct answer. And in particular, what I want you to remember and to tell me is, why do we have these techniques to begin with? Okay, what are these techniques doing for us? Why did we study them? And hopefully you would come up with the following answer. Because we were solving non-homogeneous linear differential equations. That's what these systems allowed us to do, or these techniques. Laplace transform, in particular, was deployed with non-continuous functions, right? Non-homogeneous equations with discontinuous functions. And undetermined coefficients was deployed when you had non-homogeneous stuff with like sines and cosines or exponentials. But these techniques exist to help us solve non-homogeneous differential equations. So here's a homogeneous equation. We didn't need these techniques to solve this. Although you could, of course, use Laplace transform if you wanted to, right? But you don't need to. So the theory of homogeneous equations is perfectly understandable without these techniques. However, as soon as I start having free-floating t stuff, right, this cos t here instead of a 0, suddenly now we need a new technique to deal with an equation like this. So this equation here can be solved with any of these three techniques. But in particular, you needed at least one of these techniques to solve an equation like this, something non-homogeneous. So unsurprisingly, when you start talking about linear systems, these techniques are used to solve non-homogeneous linear systems. So consider the following system, okay? This plus 2e to the negative t and this plus 3t were not allowed before. So before, we've been studying homogeneous systems. Homogeneous means no free-floating t stuff. But when you have a non-homogeneous linear system, you can have crazy t stuff off by itself if you want. And then you just have something non-homogeneous. So notice that this piece here, like this slice that I'm circling, notice that this by itself is homogeneous. Right? This looks exactly like what we've been dealing with for a week and a half now. But when you tack this garbage on at the end, suddenly now you still have a linear system, a linear first order system. It's just not homogeneous anymore. So not homogeneous, and in particular, we can still model this sort of system with a matrix equation. So this chunk right here, I can't highlight just what I want, but this stuff that I'm circling here, notice that corresponds to this stuff up here, right? The homogeneous stuff. Then you have a column vector added on at the end, modeling this first row. You have 2e to the negative t, and in the second row you have a 3t. So now we want to solve systems that look like this, that look like vector prime equals matrix times vector, but then plus a column vector that has t's in it. So before we were doing like x prime equals matrix x plus the 0 vector, if you like. And now we've replaced the 0 vector with stuff with t's in it. So again, if we were in class, I would have this on the board and ask you, how do you think undetermined coefficients or variation of parameters works to solve something like this? And I'm hoping that you would, after a bit of thought, come up with the following strategy. You would say, well, it probably works just like it did in chapter 3, and you would be right. So in chapter 3, what did you do? The first thing you did was you solved the homogeneous version of this equation. So replace the floating t stuff with just a 0 vector and solve just this little chunk right here. So solve this homogeneous linear system right here. And if you do that, you get something, as we've done many times now, that looks like this. Then you would probably want to find just a single solution of the non-homogeneous equation. So a single solution of all of this. And then you would guess that the general solution is vector x is c1 vector x1 plus c2 vector x2 plus a capital Y vector. So in other words, all I did was I took this equation from chapter 3 and bolded things, didn't I? This is now a vector, a vector, a vector, and a vector. And for this particular system right here, these are column vectors of length 2. So again, if you had to make a guess as to how the theory translated to linear systems, this is the exact thing you would guess, and you would be right. That's exactly what happens. So before I show you how this plays out, let me now just ask you, well, what do you think about Laplace transform? Okay, so we're going to see the the undetermined coefficients play out here. But before I do that, let me just ask you about Laplace transform. How do you think you would use a Laplace transform to solve this system now, when you have matrices floating around, when you have a system? And your answer would be, well, it probably works just like it did before. you're going to take Laplace transform both sides. Presumably, before we had to think about Laplace transform of y prime. When I have a prime, but it's on a vector, presumably there's a way to take Laplace transform of vector primes now. And guess what? There is, right? And then you would isolate Lx, and then you would invert the transform, be done. All right? It works just like chapter 6. So presumably there's a way to handle Laplace transform of x prime, this little piece here. This matrix here is a constant matrix, so that would pull right out of a transform, right? Because constants always pull out. And then you'd have written right here Lx. And then when you take the transform of this column vector here, presumably you just transform the individual components. So you transform top, then transform bottom. Presumably that's what you do. And indeed, that is what you do. Okay, and the last thing I want to say before leaving these slides is variation of parameters also translates. It's a general method that in principle works always, but in practice works seldom, just like back in chapter 3. And the reason that it works always in theory but not always in practice is because it involves integration. So you can look at the book to see how that integration goes. I am not going to test you or homework you over variation of parameters in this context. But rest assured it works, and the book, if you're curious, will show you how it works. But undetermined coefficients and Laplace transform is enough for us for now. Okay, so yeah. So what we're going to do now is we're going to go to examples 2 and 4 in the book. Example 2 solves this system for you using undetermined coefficients, and example 4 solves this for you using Laplace transform. So I'm going to just go to the book and walk you through the examples in the book. So if at this point in the video you want to just turn this off and read the book, that's perfectly fine, of course. The reason that we're going to the book is because I don't have time tonight with a child screaming at me to type up my own examples, right? But the examples in the book are perfectly fine. If you are comfortable reading them on your own, that's fine. But if you would like my soothing voice to walk you through them in this video, if you find it helpful to have somebody walk you through examples, then I'm now going to go to the book and walk you through the book examples. Okay, so here is example 2. Notice this is the exact system I had on the slides, and they're going to solve it using undetermined coefficients. Okay, so first things first, notice they take this 2e to the negative t, 3t vector, and write it like this. They write it as a column vector times e to the negative t, where you have 0 in the bottom, to keep track of the fact that e to the negative t only shows up in the top row. And then a column vector, constant column vector times t, where there's a 0 up top now to keep track of the fact that t only appears in the bottom row. So they call this guy here g of t, and they break it into a sum involving an e to the negative t and a t. The reason they do that is because just like in chapter 3, if you want to make a guess as to what your solution looks like, you would want the e to the negative t and t separated and make separate guesses for each one of those terms. Okay, so the next step is here, they're solving the homogeneous version. So they find the eigenvalues, and sorry, they already did the heavy lifting on a previous page. So let's go look at that real fast. So right here in example 1 uses a technique that we're not talking about and that you don't need to know. Okay, so don't worry about what they're doing here with this, matrix T they're forming. Just notice here that in example 1, they get the eigenvalues here, -1 and -3, the corresponding eigenvectors. So here is the solution of the homogeneous version. So this is a 2x2 system up here. You got 2 distinct eigenvalues, which means everything flows as easily as possible, right? Your answer is C1, eigenvector 1, e to eigenvalue 1, t, C2, eigenvector 2, e to eigenvector 2, t. So here's the homogeneous taken care of back in example 1. Okay, but the key thing to take away from this is that -3 is an eigenvalue, as is -1. Therefore, in your homogeneous setup, you already have an e to the -3t here and an e to the -t here. Okay, so keep that in mind. So back over here in example 2, notice that e to the -t appears over here on the right-hand side. So just like back in chapter 3, you might be tempted to search for something of the form constant times e to the -t as a guess, as an undetermined coefficients guess. But just like back in chapter 3, you can't do just that because we already have e to the -t showing up in the homogeneous solution, right? Here's e to the -t showing up in the homogeneous solution. So if you already have it showing up there, you can't then make a guess of that in the non-homogeneous case. That is why the book does the same trick we did in chapter 3. It says, fine, we can't deal with an e to the -t by itself. We're going to make a guess of this form. So constant vector times t e to the -t. Constant vector e to the -t. Add those up. That's going to be our guess that tries to fill in this, that tries to match this somehow. And then over here, when you have a t, well, that's just a linear function, isn't it? Right? F of t equals t is just a linear function. So they're going to assume a linear function that looks like this, constant vector t plus constant vector, to try to match up with this. Okay, so again, just like back in chapter 3, when you were doing undetermined coefficients, you make a guess as to what your particular solution looks like, and you make that guess based on what's written on the right-hand side, based on the non-homogeneous stuff, but also keeping track of the homogeneous stuff you already found. Okay, so in this case, you want to match up e to the -t, but you can't guess constant vector times e to the -t because that's already covered by the homogeneous case. So you got to do this little trick. And then here, you're trying to match up a linear function t, so you guess a linear function. But, you know, your constants in your linear function have to be vectors now, column vectors. So what happens now is you've guessed a solution like this, so you substitute it back into the original equation. So you come trucking back up here, you substitute into this equation and see what you get. Okay, so you got to prime all this stuff, right? You got to take the derivative of all this stuff and plug it into the left-hand side. So you got to product rule this stuff, this t e to the -t. The negative come down here, so you get -b e to the -t. You get just a plus constant vector c right here, and d disappears. Okay. Then you take all this, plug it in for x, and you of course still have this sitting here. So you would just plug everything in. So they did the algebraic work for you. If you have trouble with the algebraic work, or you have any confusion of what happens here, you should write this out yourself. Okay, they're just claiming that once you plug everything back in and you collect like terms, you get the following things. Okay, so what they're saying is plug everything back in and compare, like, you know, t e to the -t coefficients, compare e to the -t coefficients, compare t coefficients, just like you did back in chapter 3. Right? That's how you determined your coefficients back in chapter 3, comparing like terms. So you should write those equations down, right? And make sure that you agree with this. But this is what will fall out of that. So if you compare like terms, you're going to get the following 4 equations. That matrix A times constant vector A from there is -a. AB equals A minus B minus the vector 2, 0. AC equals -0, 3. AD equals C. So then you just got to process what all this is telling you. You have to work out what constant vector A is, constant vector B is, constant vector C is, and constant vector D is. So you just have to sort of trace through what these 4 equations are saying to nail down these 4 constants. So once again, let me emphasize, this is working just like chapter 3. It's the exact same thing. It's just now, instead of a literal constant number A, you have a constant vector A. In this case, a column vector with length 2. The same thing for B, C, and D. So the first equation here is saying that Vector A is an eigenvector of matrix A with eigenvalue -1. Right, you all agree with that. This is saying that capital A takes little a to a multiple of itself, in particular negative itself. Okay, well, if you look back at example 1, they already told you what the eigenvalues and eigenvectors are, but that's fine. So recall that the eigenvector for the eigenvalue -1 was just anything that looks like this. So just number, same number. Okay, so now you have to do a little bit of work here, and you figure out that the second of these equations, this one right here, only works if you choose 1, 1 right here. Which, if you flip back to where the book just found these values for you, right? That's the canonical eigenvector it shows anyway. This is the eigenvector that Wolfram would have spit out, right? So you can go to Wolfram and ask it for eigenvalues, eigenvectors here. 1, 1 is what it spits out for the second eigenvector. Okay, so back over here, we've chosen A to be 1, 1. And once we've chosen A to be 1, 1, we can figure out what B is from this equation. So it just sets off a chain reaction, you know. So once you know what A is, you can figure out what B is. And once you know what B is, this equation here, you can figure out what C is pretty fast because there's only a C here. And once you know what C is, you can figure out D. All right, so it's all just going to chain off here, chain reaction. So this equation here is saying that, so in this case, lowercase b, the vector b is any multiple of 1, 1 minus 0, 1. So pick whatever you want. So particular 0, -1, that's fine. So again, if you plug 1, 1 in right here, this is what you will learn, that b is any multiple of 1, 1 minus 0, 1. So just do the matrix multiplication and confirm that for yourself. Okay, so the book here suppresses all the, not all, but some of the algebraic computations. So again, if this confuses you, if you write it out and you can't see what it's saying, just email me, okay, or ask me on Friday. Okay, so this equation here, you can learn pretty quickly that you can choose little c to be 1, 2. And once you know that C is 1, 2, you can plug 1, 2 in right here for C and learn that D is -4/3, -5/3. Okay, so again, the book suppressed some of the computations here, but trust me, you can do those computations. But if it ends up that it confuses you, that's perfectly fine. Just let me know, okay? So once you've done all that computational algebra there, you learn this, that way back up here in this original guess we were making, this constant vector A is 1, 1. Constant vector B can be chosen to be -0, 1. Constant vector C can be chosen to be 1, 2. And constant vector D is 4/15. Yeah, I'm not sure why they decided to pull that 3 out there, but whatever. -4/15 is what you get. Okay, so what I hope you've taken away from this example is that even though the computational algebra might be intimidating, you know, like this might look intimidating to you, that's fine if it is intimidating to you, okay? But even though it might look bad, this is the same thing as chapter 3, okay? It's the same exact idea. You make a guess. Your guess involves constant coefficients that you have to determine. The way you determine them is by plugging back into the original equation, grouping like terms, making comparisons, and then filling in what those constants have to be after making those comparisons. Okay, so again, if any of this confuses you, please let me know, preferably via email as soon as possible, but if that's not possible, then on Friday in class. Now, let's move on to example 4, which is, and by the way, here's the variation of parameter stuff. There's the integral. This takes a while to explain. Okay, so it's not worth the time. We will skip over it. But you can see, they still give you sort of a general formula. It's just got matrices in it, you know, so it's kind of hairy. Okay, so Laplace transforms. This will not take as much time as the previous example. This is shorter. Okay, so the punchline here is that the Laplace transform of x prime is the S times the Laplace transform of x. So the book likes to emphasize that you've translated from t's to s's. The book likes to write this rather than Laplace of x. Okay, but keep in mind it's the same thing. Minus the value at 0 of your solution x. So just like in chapter 6, if you want to use Laplace transform, you have to have an initial condition. So what they do in this example is they will say, let's just assume that x of 0 is the 0 vector. Okay, so that's a perfectly fine initial condition to slap on if you want to use Laplace transform. Okay, so let's use Laplace transform on this guy. So this is the same system as before. We're just going to use a different method on it. So notice when I Laplace the left-hand side of this, I get this formula from up here. Went really fast. So Laplace of x prime is s Laplace of the left of x minus x of 0. And then this matrix A is just constant, so it just rides along, just pulls out of the Laplace, and then you have Laplace of x here. Right, remember, again, x of s just means L of x. The book likes to make this s translation explicit. And then you have to transform this guy, transform little g, to get something in terms of s. Okay, so when you transform this guy, you just go to the table, and the table gives you these two values. So you just transform each individual component of this column vector. Man, this thing skips around really, like, emphatically. Okay, so once you make your choice that x of 0 is the 0 vector, you get s xs equals axs plus this stuff. And then notice that the book's next step is it subtracts axs from both sides. So you have sxx xs. That is hard to say. sxs. Okay, man, this was not written to be spoken aloud, I guess. That's why I say slx, I guess. I don't know. Anyway, so you got this little dude right here minus this dude right here. And this x of 0 is gone, right? But if you have this minus this, notice there is an xs in both spots, so the book just factors it out. So what you're left with is a minus a, because you scooted this over, and just an s, but remember little s is like a number or something. It's a variable number. It's not a matrix. So when you pull the x off of a number, you have to have this identity matrix here. So this is what you get. So you need to isolate L of x, which remember again, this is Lx. You have to isolate that. And to isolate it means you got to take this matrix and invert it and put it on the other side. Right? You sort of have to like divide by this matrix, which means multiply both sides by the inverse, and you end up with this expression. So now you have to remember how to take inverses of 2 by 2 matrices. So notice that Si minus A is this. So where's my matrix A? It's way back up here, right? That's A. And so you're subtracting that off of an Si matrix. So Si is just S's down the diagonal. So Si minus A is this. Wolfram will most likely invert this for you symbolically, but if you don't remember how that goes, to invert a 2 by 2 matrix, you take 1 over its determinant, and you multiply bottom left and top right by -1, and you swap these two entries. Okay, so that's not terribly important. Again, if I think Wolfram will symbolically invert this for you and tell you this. So there's the inverse matrix. So you have the inverse matrix times GS, where again, GS is, where is it? Right here. So you take this inverse stuff and multiply by this, and this sort of gross thing is what you get. Okay? So it looks gross, of course, like all Laplace transform problems look gross. But focus on the big picture here, all right? You started just like in chapter 6 by taking Laplace of both sides. You got this. You need to isolate XS. Well, how do you do that? Well, you got to group the XS terms together, factor stuff out, right? And then like divide by it. That's all this is, really. You're dividing by that term to get it over. So now, once you've written this equation down, you have to invert this right-hand side. But you can't invert it until you do the matrix multiplication here and see what you're trying to invert. And that's what happens here. So you multiply everything through, and now you can see that to invert stuff, okay, I got to invert this stuff up top and this stuff down below. Okay, now at this point, after we've done this work, we're tired of doing work, aren't we? So the book here says this can be done by expanding using partial fractions in table 6.2.1. You can do that. You can plug these into Wolfram and ask for the partial fractions expansions. Wolfram will actually will compute an inverse transform for you. I didn't tell you that in chapter 6 because I didn't want you doing it back then, because I wanted you to use the table. But now we've done enough work, haven't we? I mean, let's just use Wolfram now. You can just plug this entire thing into Wolfram and get its inverse without any partial fractions work. Same thing for this. If you want to, just Google inverse transform calculator or something, and Wolfram will be a top hit. You can just plug that function right in, and what you will end up getting from Wolfram is this expression. Okay, so we actually have only covered half of this section. Oh man, this is a long section, okay, but don't lose the forest through the trees. Laplace transform and undetermined coefficients are what you want to take away from this, so don't worry about the other half. And what you should take away from Laplace transform and undetermined coefficients is that it works basically the same as chapters 3 and 6. It's just more obnoxious now because you got matrices, so the computation is worse, but the idea is the same. So don't lose the forest through the computational trees, and I hope this was helpful.